Hi, I'm Kassim. I work for a company called Exergy. We're just situated just in the other building at the technology park. We collaborate on quite a few projects with Coventry University. One of the first projects we collaborated on was RESSEEPE, approximately 4 years ago. So our role, Exergy's role in this project, we're the scientific and technical coordinators of the project. So the RESSEEPE project has two main coordinators, the administrative and financial, and the scientific and technical. Our company Exergy, we do the scientific and technical. So we make sure all the technical side of the project is going smoothly, all the technology selections are appropriate, let's say, for the demo sites. So we overlook the whole situation, see if everything's going smoothly and making sure everything goes well. Before I start my presentation, we want to show you a short video, short project video we've created. We're nearing the end of the project now, so we're coming to a time where it's the dissemination and the exploitation of the project. So we created this video as part of the project, and I hope it will give you a more clear understanding.
RESSEEPE Project. Nowadays, public buildings have a huge impact on the total energy use in Europe. The EU, through the funding of the RESSEEPE project, aims to reduce this energy consumption and, in consequence, to reduce the CO2 emissions due to public buildings. RESSEEPE is a 48-month project. After the development of the diagnostic methodology, retrofitting and energy efficiency technologies are designed and demonstrated at building level in different demo sites. At the end of the project, the impacts of the technologies developed were assessed and their replicability evaluated. The main outcomes of the project were a combined decision and design-making tools for improving the building performance through retrofitting. This approach to lower building running costs and provide a technological affordable cost of entry. A standardized low-energy concept deployed in the demo sites and the best practices approaches highlighted in a book. Several remarkable innovative technologies and materials have been integrated into the retrofitting process as an existing technology, improved or new prototype design. RESSEEPE demonstration sites. The first demo site is Balderskolan Secondary School in Skellefteå, Sweden. The second demo site is composed by 2 hospital districts in Barcelona, Spain. The third demo site is composed by 2 buildings in Coventry University, UK. The efficient technologies included are Balderskolan Secondary School, external thermal insulation composite system, vacuum insulation panels, high energy efficiency windows, switchable electrochromic windows, LED lighting, Consorzi Sanitari de Terrassa, external thermal insulation composite system, thermal solar plant for DHW production, high energy efficiency windows, LED lighting, Corporació Sanitari Park Tauli, EPSG panel installation, thermal solar plant, high energy efficiency windows, internal and external LED lighting, Richard Crossman building, solar PV panels, high efficiency glazing, curtain wall, roof improvement, LED lighting, BMS Building Management System, John Lang Building, EPSG panel installation, aerogel-based super insulating mortar, vacuum insulated panels, ventilated facades, building integrated photovoltaics, PCM phase change materials, EC film, RESSEEPE KERs. Successful experiences of the project. All technologies have been tested and pre-qualified. The performance reporter and decision support tool retrofitting planner at the building and district level have been developed and tested. The prototypes developed have been fully designed, manufactured and tested in the demo sites.
I hope that's made the project a little bit clearer. So basically, I'm going to run you through some of the innovative technologies we selected within the RESSEEPE project. We consider these as key exploitable results because they started within the project. They started at a very, very low technology-ready level. During the project, they progressed quite well, and we've managed to demonstrate these technologies actually on the demo sites. So these are some of the technology we've selected for the RESSEEPE project. We decided to choose different type of technologies rather than sticking to, say, external insulation. So we decided to go for some envelope elements, some building services, some lighting, and some renewable technologies as well. As you've seen previously at the John Lamb building, we had aerogel mortar, vacuum insulated panels, the ventilated facade, which I'll explain a bit later on in the presentation, building integrated photovoltaics, electrochromic glazing, and high efficiency glazing as well. Regarding building services, we had HVAC system optimizations, PCM cooling and storage, and seasonal thermal storage. We chose LED lighting along with solar thermal collectors and solar PV panels. So let me quickly talk you through the ventilated facade I think you saw at the John Lamb building, which was the middle one. The ventilated facade is a construction system consisting of different elements. So within the system, we have building integrated photovoltaics, which were at the front. And we had an air gap for ventilation, and then we had vacuum insulated panels that were attached to the wall directly. This system is a very, 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 say, well-performing in the sense that it provides different say, energy measures and savings as well. Some of the advantages are they avoid thermal bridges. It has a very, very good thermal and acoustic performance, considering we're using vacuum insulated panels, which is a very, very good technology. We're producing electricity right now. We didn't have a chance to see, but the PV panels are connected inside the lab downstairs, just below the ventilated facade. So in that room, we have the inverter, we have the batteries in there, which at the current moment, we have a loading connected, a light bulb load, just for testing purposes, to see if the solar panels are actually producing some energy. So we'll be having results for that at the end of next month, which is the end of the project, hopefully. So the next technology was aerogel-based super insulating mortar. This is a silicon-based product. I think it's 1% silicon, 99% air, I think it's something like that. So we decided to mix this into a mortar and decided to install this at the John Lamb building. As we mentioned previously, the John Lamb building was used as a lab scale testing site. So some of these innovative technologies we thought would be, say, well tested at the John Lamb building. So this is one of the technologies we installed. I think Monica will cover the installation procedure, but it was a very, very, say, difficult technology to install, as not a lot of people know how to install this technology or know about this technology. But this will be covered later on. PCMs, I guess you've had a lot of information about PCMs today. They basically store and release thermal energy during the process of melting and freezing. Obviously, when they freeze, they release large amount of energy. When they melt, the energy is absorbed, going from the state of solid to liquid and back again. Vacuum insulated panels. I'm not sure if you can see through the ventilated facade, but it's a foil based material. So the core material is in a foil envelope. The core is a fibery material. It's quite powdery as well. So the company decided to use it as a vacuum. So we took all the air out, vacuum packed it. Doesn't allow air to go through at all. It's high efficiency in insulation and has a very, very low thermal conductivity. So this is a very, very well-performing technology, and we are seeing this in the results at the moment, and hopefully we'll be seeing them in our final analysis. I think Monica has a few examples there she'll be passing around. That's the aerogel mortar. That's the mixture it comes in. So the powder stuff in the bag, that's the aerogel mortar. You just have to add water and then it's ready for installation. So while you guys are looking at the samples, I'm going to carry on. I'm going to continue. I guess we'll stay on time. Yeah. Right, another technology that was made as a prototype in the RESSEEPE project was electrochromic windows. This was done by a partner in Switzerland, if I'm not mistaken. They created their own EC window. They did their testing in the lab for this. Unfortunately, it was not ready for demonstration testing, so they could not make an electrochromic window for building size for a normal window. It was roughly around this big, 30 centimeters by 30 centimeters. So we could not put that at a demo site to install and do the testing. So they did some lab testing, and they found that it was very, very efficient. It reduced energy expenses by 19% and 48% in cooling and lighting demand as well. This was the prototype. For demonstration purposes, we decided to get a commercial product, which they said, or they claimed to be far more different to the regular electrochromic windows they have in the market. So we're currently testing this at the Skellefteå demo site. Another partner in the project, UPC from Barcelona, we're working on a prototype for a new solar thermal collector. This solar thermal collector had a transparent insulation material. As you can see in the diagram, it's right there in the middle, between the glass cover and the absorber. So that's where they put it. That was their innovation. They're currently testing that at the Barcelona demo sites as well. So the monitoring for that is happening, and we're getting some results in as well. It's said to be, if I'm not mistaken, 30% more efficient than a regular solar thermal collector, if I'm not mistaken, yeah. So this is said to be 30% more efficient than a regular solar thermal collector. So hopefully the results will come through, and you'll be able to see in the coming months the real effect. So I'm going to move on to the diagnosis methodology, how we went about selecting the correct technologies for the correct demo sites. Obviously, we had 3 demo sites from 3 climatic conditions. Some technologies, for example, a solar thermal collector would not be suitable for, say, a colder climate, because it would not be as efficient. So to diagnose the technologies we need, first we looked at the European building stock in the current market right now. We saw that across Europe, most of the buildings were inefficient, and there was not a lot of planning on retrofitting. So there was a lot of room for improvement for buildings, and we documented this in the project, and we took this forward for our research. So when it came to looking at technologies, we had to think about it at a district scale, not just domestic level or public buildings. We had to think about not only the technical impact, but the social impact as well. If we do install these technologies, yes, we'll be saving on energy efficiency, but what will the comfort level be of the rooms? Will occupants be satisfied with these technologies? This is some of the testing we did quite recently as well, with post-retrofit questionnaires and surveys, which Monica will cover later on. When it came to selecting technologies, this is the criterion, or some of the criteria we took on. So we looked at installing the technology not at a technical level, but we took on other criteria as well, such as the operational and maintenance requirements of the technology, the structural limits of the demo site, the architectural barriers of the demo site, local regulations. Another big thing that came into mind was, are we able to get contractors to do these installations? Because some of these technologies were very, very new, very, very innovative. We found that not a lot of contractors were willing to take on the installation because they were scared, basically. They did not know how to work with it. So these are some of the criteria we took on. And from here, we created a matrix, a demo site matrix. So each demo site was given this matrix with a criteria and a score out of 5. So the demo site owners, the scientific experts, the technology providers got together, worked on this matrix, and as a collective came up with a solution basically on which technology is best for each site. So I'm not sure if you can tell from this image, I don't know if it's clear enough, but you can see the cumulative vote at the bottom. You can see a couple of ticks, a couple of crosses. That shows that some technologies are good enough for the demo site, some are not. So from here, these are the technologies that were chosen. I went through this earlier on. And okay, so now we've chosen our technologies. We've selected our technologies for each demo site. They're all set in stone. How do we know they're going to be, how do we know it's going to be a good decision to install these technologies? So before we even went about installing these technologies, we had to do some simulations to prove that, okay, the energy efficiency will be improved. There'll be significant energy savings. So we created BIM models, then we created IES models as well. So we created so first we did a pre-retrofit simulation. So we did simulations on how the building is right now. You can see from the left-hand column, that's some of the results we got. Then we did a post-retrofit simulation. A post-retrofit simulation is where we do simulations based on the actual installation that is going to happen on site. So as you saw in the John Lamb building, the 6 technologies that were installed, we did that exactly how they are right now and ran simulations like that. Going forward, for more research purposes, we decided to do a full extrapolation of the building. So if we did have enough, say, money, enough investment to cover the whole building in these technologies, what would improvements be? So there's the results for the 3 simulations. As you can see, Richard Crossman building was an actual full retrofit, a full building retrofit, because majority of the building, or the external of the building especially, was changed and improved. So with that, the simulations gave us 49% savings, which is very, very close to the target of the project. John Lamb building was significantly lower. This is due to John Lamb building being used as a testing site for the new technologies. We didn't know how these new technologies were going to perform before, because the technology readiness level of these technologies were very, very low. They have not been tested before. So John Lamb building was used for this. This is just the simulations. We're expecting the results to be far better in real. We did this at the demo sites in Spain as well. So we got savings of 25% and 46% respectively at the Barcelona demo sites. And Skellefteå as well. We did the testing at Skellefteå, and unfortunately the savings were not as high. It's approximately 3.3%. This was due to the Skellefteå building being very well insulated to begin with, as they're a Nordic country. Very, very cold climatic conditions. Their regulations are very, very strict in that sense as well. So their insulation was very, very thick. I think the sample we saw of their walls was 500 centimeters thick. Yeah, the walls are 500 centimeters thick, and these are the older buildings as well. So I imagine the newer buildings to be much more efficient. That's all from me. Thank you.